Hello, what's up, audience? Welcome to discuss the questions of coordination compounds. We have some questions and their solutions or answers. So welcome and keep attention. You can take a note in order to make much discussion which could be intensive and make you capable to solve these questions. Okay, we have 6 questions here which are very common and they are likely to be asked. And the first question is the meaning of a spectrochemical series. Another one is to identify low and high spin ligands in the spectrochemical series. Also, we have a question to identify paramagnetic and diamagnetic complex compounds, as well as qualitative and quantitative analysis. Also, we have primary and secondary data. We have to study it. Also, we have to explain the geometry of complex compounds, different geometry we have. So we are going to discuss them. Also could explain a little bit about the coordination theories. Welcome very much. Pay attention. Okay. What's the spectrochemical series? This is the order of ligands based on their strength. And this strength could discuss it much in the crystal field splitting theory, which could explain the spectrochemical series. But there are 3 tips you have to understand in this concept of spectrochemical series. First of all, have the word spectrum. That in word spectrum means the band of colors, and the meaning of chemical is just the species, you can say, a distinct compound or substance. Also have series. While you ask about series, you should have to understand the arrangement or the order of those compounds. And this is the spectrochemical series, which is arranged in the order of increasing its strength and causing splitting of the d orbital. We are going to discuss it when we are going to discuss crystal field theory. Okay. Question number 2 is how can we now identify low and high spin ligands in the spectrochemical series? First of all, we have to understand the low spin and high spin ligands, what are they and why they're called low spin and why they're called high spin. Okay, first of all, we have to trace back the quantum numbers that we've studied in the general chemistry. You can say is the one of the quantum numbers called the magnetic spin. Spin quantum number. Apart from magnetic quantum number, in that order we have spin quantum number. In the spin quantum number, we have the value of plus a half for the electron which is spinning in the clockwise direction, and have minus a half in the direction of electron spinning in the anti-clockwise direction. So basically, what's the low spin complex? The low spin complex is that one have the few number of unpaired electrons. So that complex will having such character is called the low spin complex. And the complex having the few number of unpaired electrons actually will have the low resultant spin. And while we are talking about the resultant spin, now we are just taking the electron which is spinning in clockwise direction have the value of plus a half. So if we have the value of plus a half, the resultant spin is to take the number of electrons which are unpaired and which are spinning in clockwise direction and multiply them and multiply them by a half, meaning the value of clockwise spin is plus a half. So if you are going to count the number of electrons, example in this complex which is hexacyano cobaltate 3, it has no any electron which is unpaired. So the spin value or the resultant spin will be a half times 0, which equals to 0. So it is a low spin. And from this example, which is example for cobaltate 3, has 1, 2, 3, 4 unpaired electrons. So these 4 unpaired electrons, these have a plus a half value, plus a half spin value, and plus a half, plus a half. So if we're going to add them, we could multiply by 4. We could get 2. So this resultant spin has 2, and here the resultant spin is 0. So this is a high spin, while this is a low spin. That's the meaning of low spin and high spin complexes. Now, let us turn into ligands. So those ligands which forms high spin are called the high spin ligands, like this one. And those ligands like cyano, which forms complex with the low spin, are called the low spin ligands like cyan. And basically, their ability to cause splitting in high energy separation, or to produce the degenerate orbital, to split the degenerate orbitals to make them in high separation distance, so or high energy level distance. It's called low spin ligand because it results into electron pair favoring to take place more than electron arrangement in these orbitals as well. This is a concept about low and high spin ligands. Also, we have a question: what are paramagnetic and diamagnetic compounds? Actually, the paramagnetic behavior is the tendency of a substance or an object to be attracted with a magnet. So the magnetic material, maybe you can say, if you have a paramagnet and you have a paramagnetic material, that paramagnetic material will be attracted with that magnet. So simply can say complex which can be magnetically attracted are called paramagnetic. But diamagnetic will be the opposite of this concept. And the paramagnetic complex or materials have the resultant spin not equal to 0, because if it will have the resultant spin of 0, means there is no any unpaired electron. But if it has the resultant spin which is greater than 0 or is not equal to 0, means they have at least one unpaired electron. That material will be called paramagnetic. And here you can see also we have ferromagnetic material which has the many number of unpaired electrons or have high spin value, which we are calling it high resultant spin. I think I've told you that diamagnetic material is the opposite of paramagnetic material, and even the examples are the same. And here we have this slide here. So here it is flow. This is paramagnetic. This is diamagnetic. Well, this was a fluoride. Here it is fluoride. Yes, here's fluoride, which is a paramagnetic one, which has in this previous slide here. In this slide, in this slide behind, has a fluoride. This one, cobalt fluoride, has this resultant spin, and it has unpaired electrons, which make it to be paramagnetic material. So this is paramagnetic, while this is a diamagnetic material. Now we have another question: what is quantitative and qualitative analysis? Then what is the primary and secondary data? Actually, quantitative analysis has measurable data which can be numerically expressed. Example, if you want to measure weight, you can express the weight by using the unit of weight like grams, kilograms, and so forth. And here you can be asked how much that index has been evaluated. So quantitative analysis is collecting and evaluating numerically measurable data, while the qualitative analysis is based on subjective judgment. Example, you can say the sample was sweet, the sample was odorless, the sample was smelling like a rotten egg. So those are qualitative analysis. You're just making some judgment based on the particular phenomena, but that is not numerically measurable. Cannot tell us it is the sample was sweet by how much. That is a qualitative data. That is in contrast to quantitative data, which could you can numerically express it. Okay. Here also have primary data and secondary data. If you're talking about primary data, this data is obtained directly from the field of investigation. Example, if you are going to perform titration in laboratory, after performing titration, you can take the unit, or you can take the results from your titration experiment. that is a primary data because you obtained it directly from the investigation field or from the experiment. So this is called primary data. But secondary data, you can use data which has been generated for someone else, not you. So you didn't attend to the field. Other person may have those data, and you can request them to give you that data. That is called secondary data. Okay, let us say hybridization versus geometry. If you are talking about geometry, you're talking about shape, and if you're talking about hybridization, is the way those orbitals, we are saying those orbitals participating in bond formation are combined, right? So here we have SP hybridization, which could give us linear geometry. We have SP2, which can give us trigonal planar, and we have SP3, which could give us tetrahedral, and we have DSP2, which could give us square planar, and have SP2, which could give us trigonal planar also, and we have SP3, which give us trigonal bipyramidal, and the D square SP3, which could give us octahedral as well. This is D square, but in other way can be SP3 D square. So you can give also octahedral. That's why you can see we have the outer complex and inner complex, and that is caused by this hybridization difference. Okay, we have question number 5, which asks to explain types of geometry in complex compounds such as linear, square, planar, tetrahedral geometry, etc. And this is an example of linear geometry compound, which is diamine silver 1. This one is our example of linear complex, and this has a hybridization of SP. And this one is cisplatin. Cisplatin is a square planar complex. This is one example of square planar complex. So the way we can explain it is you can explain by using hybridization, and you can give examples this way. We have tetrahedral and octahedral. The tetrahedral compound like this one, it is a tetracarbonyl nickel, and tetracarbonyl nickel has the tetrahedral structure, and its hybridization is sp3. And this one is octahedral complex, which has 6 coordination number. It is called the hexacyanoferrate 3. Hexacyanoferrate 3 because it has charge of 3 here. So also it is called this, sometimes it's called this ferricyanide. These are some common names which are used in technical way. They are called ferricyanide. Okay, here we have to explain coordination theories. There are some theories which are describing the way bonds are formed in complex compounds, or the way ligand interacts with centromere atom. So in coordination theories, there are several concepts which tries to explain about the way that bond is formed. We have the first man, or the first scientist, who tries to explain it by saying that metal to ligand have some ways to interact. This man called Weiner, and he told that itself centromere atom has 2 types of valences, and the first type of valence is called the primary valence, and the second one is called the secondary valence. So the primary valence is kind of valence that we really know it. We know valence is the combining power of an element, right? So that primary valence is what we normally understand it as a ionizable valence. So you can say the valence that we are counting it by looking the charge of the centromere atom, charge of an element. So that is a primary valence, which can be ionized. Example, if we are talking about iron 3, so the primary valence for that could be the could be 3 because the combining power of iron 3 is 3. So the primary valence that can be accounted by the ionization chances. Okay, we have secondary valences. The secondary valences, this was non-ionizable, and this was accounted for those empty orbitals. So these secondary valences explains the availability of those empty orbitals. Could be the valence of that, the secondary valence of that metal. So basically, to know how much secondary valence is present in a particular metal ion, we should have to check the empty orbitals, empty d orbitals available in it. Okay, we have another theory explains the coordination compounds, and it's called the valence bond theory. Simply, the valence bond theory explains the interaction of two partial filled atomic orbitals. Example, if we have one atom which is a partially filled. Example, let us say hydrogen have one electron, right, in its orbital, but it needs another electron to complete its orbital, and another orbital, maybe another atom is hydrogen having a single electron in its orbit. So they have to interact in order to share those electrons to complete those orbitals. So the main concept of valence bond theory is the overlapping of those atomic orbitals which are incomplete. That is the concept of valence bond theory, and he portrays that this concept appears to the coordination. Now, what is the crystal field theory? If you're talking about crystal field theory, we describe the breaking of orbital degenerance in a transition metal complex due to presence of ligands. Actually, here the important thing to understand is the degenerance. If you're talking the orbital degenerance, we mean that orbitals having the same energy level. So if we are breaking the degenerance, means the orbital should have to split and having different energy levels. So what appears in crystal field theory says that when ligand approach the metal ion, or the metal ion, its d orbital splits to form to lose its degenerance. So the one will have a particular energy level and another will have another energy level. So the breakage of those orbitals degenerance actually allows some ions to some electrons to pair, or sometimes it allows to form some hybrid orbitals which could accept the entering of the ligands. So ligands could enter in those empty orbitals available after losing degenerance. So this is a crystal field theory, but the main concept to understand is only it breaks. The main concept to understand here is only the breaking of orbital degenerance due to ligand approaching. Then when the ligand approaches the central metal ion. And they have also molecular orbital theory, which explain that once atoms are combined, actually those orbitals of those atoms, they are combining and forms the molecular orbital where those electrons could have to arrange to form the bonding molecular orbital. Then some of them could not bond, which form the non-bonding molecular orbital, and another one could not bond and form antibonding, could bond as the antibonding molecular orbitals. Thank you very much. Remember to subscribe our channel for more videos. Thank you very much.